Hello, everyone. Welcome to the second part of my talk. I think we have three theorems to prove. The first one is that if a knot has property D, then the fundamental group of the manifold obtained by dense surgery with slope at least 2g minus 1 is not left orderable. As usual, we have two steps. The first step is to find an element without fixed points. And the second step is to prove the pre-order generated by Z is not a partial order. And the special element here is the meridian mu. Since after the dense surgery, mu to the p's power times lambda to the q's power equals to 1, and since that p and q are both positive, we have that any fixed point of law of mu is the fixed point of law of lambda. And by the property D, this is also a global fixed point, which is not allowed. Therefore, mu doesn't have a fixed point. Now we define a pre-order generated by mu, which by definition, mu is greater than 1. Since mu to the p's power times lambda to the q's power equals to 1, and p over q is greater than or equal to 2g minus 1, that means mu to the 2g minus 1's power times lambda is less than 1. This is less than 1, and mu inverse is also less than 1. So mu is less than 1 by the condition 2 for property D. Since mu is less than 1 and greater than 1, and mu is not 1, we have that it is not a partial order. Okay. Now let's look at the rest two theorems. One is the one closures of one braid base. If it's not an unknot, then it has property D. The second one is for the satellite knots. If the pattern is a one bridge braid and the T over omega is at least 2g minus 1, then the satellite knot has property D can be implied from the property D of the companion knot K. Let's first find the knot group of the one bridge base, which would be useful in both theorems. As a knot in the solid torus, the fundamental group has two generators and one relation. This relation could be written as a long formula of x's and y's, but that would be harmful. It's better to write everything as conjugates of mu and things like conjugates of mu inverse, because that we know mu is greater than 1 by the pre-order generated by mu. Then any conjugate of mu is greater than 1. If we write R mu equals to a product of conjugates of mu, we can actually throw out any element, any middle element here. For example, we can throw out G2 mu G2 inverse, and the R mu would be greater than G1 mu G1 inverse times G3 mu G3 inverse, and so on. That is all because this pre-order is invariant on the left multiplication and the right multiplication. And these G0s are words of letters X and Y's. no letter x inverse, no letter y inverse. And we can also define a G0 here. And each GIR suffix of G0 and the longitude lambda can be written as y G0 times power of mu. And the geometric interpretation of x and y and the r mu r lambda here. Mu and lambda are meridian and the longitude of the one bridge braid. This not. And r mu and r lambda are actually meridian and the longitude of the solid torus. And the x and y's represents the two disks obtained by cutting the meridional disk by the bridge. So the boundary of the first disk is the union of the bridge and the part of the meridional disk. If a loop that stays in the one bridge braid and cross the x disks once positively and goes back, that loop is represented by x in the fundamental group, and similar for y. We are not going to prove everything, but we just use this as an example. For the rest, we let omega to be 7, t equal to 4, and b equal to 2. Then we can calculate those gi's. G0 is, for example, yx, yx, y, and each other suffix of gi's. That means if we remove the first letter of G0, we get G2, and we remove first two letters of G0, and then we get G4, and so on. In the braid closure, we have the relation that R lambda equals to 1, and this would be the only relation. That implies y equals to a product of conjugates of mu. The first condition of the property D that states that if law of mu and law of lambda have a common fixed point, then it's a global fixed point. So suppose they have a common fixed point, say S, then S is a fixed point of lambda times mu to the some power. So S is a fixed point of yg0. And g0 is y, x, y, y, x, y, and yg0 is the word of letter x and letter y. X equals to mu times y. We replace every x with mu times y. That's yg0 would become a word of letter mu and y. And the thing, if ys is greater than s, then since mu s equals to s, we have yg0 of s greater than s, but yg0 s equals to s. So that's not allowed. And similarly, if y of s is less than s, then yg0 of s is less than s, which is not allowed either. So y of s is s as a fixed point of law of y. Since the group is generated by y and mu. It's a global fixed point. Now we turn to the second condition of the property D. We define the pre-order K generated by mu and mu to the 2g minus 1's power times lambda, then do an inverse. If we can prove that mu is less than 1, that means by the definition of the pre-order K, we have that mu is in the root closed conjugancy closed submonoid generated by mu inverse and mu to the 2g minus 1's power times lambda. And that's what we want in the property D. Now the genus is 10. So we have mu greater than 1 and mu to the 19th power times lambda smaller than 1. Mu equals to xy inverse. Mu greater than 1 is equivalent to x greater than y. And we can throw out two conjugates of mu in the four conjugates of mu. And then we get y greater than g1 mu g1 inverse times gi mu gi inverse. And similarly, we can throw out 3 out of 4. Then we have y greater than g1 mu g1 inverse. Now we estimate the g1 here. We first compare g1 with g3, as g3 is the suffix of g1. g1 is yxy. It is also yxg3. And we replace x with y. It is only possible because the pre-order K is invariant under left multiplication and right multiplication. g1 is greater than y squared times g3. And replace the middle y with g1 mu g1 inverse, g3 mu g3 inverse. And then we get y g1 mu g1 inverse g3 mu. And we replace the first y with g1 mu g1 inverse, and we get g1 mu g1 inverse squared, then g3 mu. Then we compare g3 with 1. We write g3 as y, and replace y with g1 mu g1 inverse, and we get something g1 mu g1 inverse to the third power times mu. And we cancel g1 here. It's possible. And do some algebra. We get g1 is at least mu to the 4th power under order Q, on the order K. Then we are going to do from yg0, which is lambda times mu to the some power. Okay, it's lambda times mu to the 30th power towards the g1 here. First, we compare yg0 with g0. We just replace y with g1 mu g1 inverse. Then we compare g0 with g2. g0 equals to y times g2. And then replace the middle y with g1 mu g1 inverse times g2 mu g2 inverse, and get g1 mu g1 inverse squared times g2 times mu. And similarly compare g2 with g4, compare g4 with g1, and the final thing here is G1 mu G1 inverse to the third power times y times G1 times mu squared. Here we replace the first G1 with the mu to the fourth power obtained by the last step. Then we get a G to the seventh power here. Okay. So since yg0 equals to mu to the 13th power times lambda, which is mu to the 11th power times mu to the 19th power times lambda, which is less than 1, and yg0 is less than mu to the 11th power. And after doing the algebra, we get mu is less than G1 mu squared G1 inverse. Okay. If instead we don't have the mu square, we just have y less than G1 mu G1 inverse. That combined with the condition y greater than G1 mu G1 inverse, we sure get something interesting. That means if we replace the 2g minus 1 with 2g, then we can get something interesting. We just have missing 1 here in the component. What we do is that we remember y equals to G1 mu G1 inverse, G2 mu G2 inverse, G3 mu G3 inverse, G4 mu G4 inverse, and cancel out the G1 mu G1 inverse here. Then we get G1 mu G1 inverse is at least the product of G2 mu G2 inverse times G3 mu G3 inverse, G4 mu G4 mu inverse. And we throw out 2 out of 3, and we get G1 mu G1 inverse is greater than G2 GI mu GI inverse for each I equals to 2, 3, 4. Then in this condition, we replace G1 mu G1 inverse with GI mu GI inverse. We get y greater than GI mu GI inverse squared. Okay, and the punchline is this condition is better than this condition, so that we can redo the whole process with this condition instead of this condition. Then we can get something interesting. There were 2 steps, G1 to 1 and also YG0 to G1. In this case, we only need to redo the first part, the G1 to 1 part. But in some other examples, we have to do the second part, the YG0 to G1 again. So now G1 we compare with G3. G1 is yx times G3, which is greater than y squared G3, and replace the middle y with G3 mu squared G3 inverse, and we get yg3 mu squared. And then we can replace the first y with G3 mu squared G3 inverse, and we get G3 mu to the 4th power. And similarly, from G3 to 1, we just say G3 equals to y, and that's greater than G1 mu G1 inverse. And after canceling out this G1 and move the G1 inverse to the left-hand side, we get G1 is greater than mu to the 5th power instead of the 4th power here. That gives the additional one. The additional one, then we get y less than G1 mu G1 inverse, and that's also less than y. And if it's a partial order, that means every middle step is an equality. And we can see that in the other way around, if it's pre-order, and suppose we have this condition, then for some middle step, we transfer that y towards the transfer this y towards the first element of the middle step, and transfer this y to the second step of the middle element, and each middle relation can be reversed. And one of the relation that can be reversed is that mu is greater than 1. That means mu is less than 1, which is what I want to prove. So that actually proves, at least for this example, that this one bridge braid is have property D. Now we show some proof for the satellite knot. In the satellite knot, we don't have R lambda equals to 1. We have R mu and R lambda here, and we have the condition that for R mu and R lambda, it has property D, and we want to transfer the property D for R mu and R lambda to the property D for mu and lambda. That also has two parts, part for fixed point and part for the partial order. And similarly, we can go from yg0 to 1 with every step in gi. We take out r mu to the 2gk minus 1's power to the times r lambda in the front, and the meridian mu at the back. And in the last step, we get r mu to the 2gk minus 1's power times r lambda to the omega's power, and the mu to the minus 2gpk plus 1 plus mu plus omega t plus b. And the mu to the omega t plus b, this part can be cancelled because mu and lambda commutes. And that gives us mu to the 2g minus 1's power times lambda is greater than r mu 2g minus 1's power times r lambda to the omega's power, which gives that if the first thing, mu to the 2g minus 1's power times lambda is less than 1, then r mu to the 2g minus 1's power times r lambda is less than 1. That should be enough. And also mu is less than 1 if and only if r mu is less than 1 from this relation. It should do the transition.